Okay, so in this lesson 6.4, we're going to look at applications of vector addition. So we're going to go through some examples of application problems where we're going to create vectors and try to add the resulting vectors and find the resultant. And this is going to require like more use of trigonometry beyond what we've done in the past. So we've done Pythagorean theorem and trig ratios, but we're going to be looking at things like sine law and cosine law as well. So here is example one. Two Bear Creek linebackers hit the Innisdale quarterback at the same time. The larger linebacker hit the quarterback with a force of 350 newtons east, and the smaller linebacker hits with a force of 200 newtons northeast. Find the magnitude of the resulting force in which the quarterbacker feels and the angle of the resulting force. So I need to create, before we can solve this problem, I need to create a diagram that represents the vectors being described here in the problem. So I will highlight what's being described. So we have a force of 350 newtons going to the east, right? That's the larger hitting the larger linebacker hitting the quarterback, and the smaller linebacker hits the quarterback with a force of 200 northeast. Okay, so you have two linebackers hitting this quarterback with two different forces in two different directions. So I'm going to represent that with my with a vector diagram. So I'm going to have a force that's acting 350 newtons to the east. So let's draw a force arrow, a vector arrow that looks like that. So that's going to be my arrow for representing the 350 Newton force. Okay, and that's so N for newtons, not north, newtons, and that's going to the east. Okay, and that hits my my quarterback. Okay, so let's say the quarterback is right here, right, and then I have another force acting 200 newtons northeast. So I'm going to find a little 45-degree angle there and show, well, I have another force coming this way. It's not as big as the 350 newtons, so my arrow is not going to be as big, but there it is, 250 newtons, and this is northeast. Okay, so how do I know that's northeast? Again, think about like, well, north, south, east, west. That's going to be northeast, just like that. Okay, so we're going to add these two vectors and find the resultant vector. Okay, and when we add two vectors, if you recall, we don't add them. Oh, my apologies, not 250, it's 200. There you go, 200 newtons east, northeast. So 350 newtons east and 200 newtons northeast. Okay, so when we add two vectors, we don't add them head to head like this in this diagram. We have to add them head to tail. Okay, so I'm going to create another diagram that illustrates that. So here is my 350 Newton vector going straight to the east. And I'm just going to take that 200 Newton northeast vector and add it on to or connect them head to tail, like this, like so. Okay, so this vector here is going to be 250 newtons. And the resultant vector is going to be the vector connected head to tail of my two added vectors here. So I'm just going to do a little dotted line, like so. Okay, and there we go. There's my vector. That's my resultant vector. We'll call that vector R. Okay, and we need to know what the angle of this vector is. What's the angle of that vector, and as well as the magnitude. Okay, now let's see what we can sort of figure out here. If we have a vector let's go back to my original diagram. If you had a vector here that's northeast, a northeast vector is directly 45 degrees an angle, either there or even down here. Okay, and then if I look at, I have a little Z pattern going on here. This is going to be 45 degrees there. Okay, and so if that's 45 degrees, imagine here now on my second diagram. Okay, so if I just sort of extended this line here, extended this line here. All right, so here I have a 45-degree angle using opposite angle theorem. Well, that's 45-degree angle over there, and then this whole diagram forms a triangle, right? So let's say, well, what about the angle inside the triangle? Well, I can just use the 180 degree complementary angle rule, right? So 180 minus 45 is going to equal 135 degrees. So that this inside angle is 135 degrees. So I need that angle, and the reason why is if you recall from trigonometry, grade 11, if you have a triangle, so here I'm just going to quickly sketch this triangle again. So if you're given a side, which is a 350 newtons, and you're given the other side, which is 250 newtons, and you're given the angle between them, which is now 135 degrees, well, that's your SAS triangle, the contained angle, right? So SAS triangle, which has a contained angle. And if you recall, we have a formula for that. We have something we can use, and that is the cosine law. So we're going to use the cosine law to help me find the resultant vector. Okay, so let's recap what the cosine law is. The cosine law is your c squared equals a squared plus b squared minus 2ab times the cosine of the angle between them, which would be angle C. So on a triangle like this, I'll sketch the triangle out again. So you could have side A over here, side B over there, and the resultant would be side C, and the angle between A and B is angle C. Okay, so let's use the cosine law to help me solve for the resultant. Okay, so let's find some space over here. So the resultant vector r, okay, and it's going to be r squared, right, equals 350 squared, 350 newtons squared, plus the other side's 200, so 200 squared, minus 2 times 350 times 200 times the cosine of the angle between them, 135 degrees. And you got to make sure your calculator is in degree mode. I know we've been using radians for a while, but you do have to make sure your calculator is in degree mode. You calculate this, and you get an answer approximately of 511 newtons. Okay, so remember, you may have to go back and look at some of your old notes to kind of review a little bit about how to find how to use the cosine law. Okay, but that's it right there. So there is my resulting force, the magnitude anyways. I do need the angle, so I need theta. So let's go back to our diagram here. How do I find theta? You might recall, okay, so we have more information now. We have a resultant, right? It's 511, and we have other angle information, so we can potentially here now use a sine law, right? So I have a side and its opposite angle, and I'm looking for an angle, and I have its opposite side. So 250 newtons is the opposite side. So I'm going to use the sine law. Again, you might need to go back and review sine law as well. So sine law says, if you have the sine of an angle divided by the length of its opposite side, that ratio is equal to the other angles in that same triangle. So sine of angle B over its opposite side length, and sine of angle C over its opposite side length, C. Okay, so to apply the sine law here, I'm going to say that, well, I need angle theta, so sine of theta divided by the opposite side, which is 200, that's going to equal the other ratio we can get is from the angle we do know, 135 degrees, over its opposite side, which is now the resultant vector, 511. Okay. Now, if I solve for theta, if you forgot how to solve for theta, well, sine theta, if I rearrange, this is going to be 200 times sine of 135 over 511, okay? And find theta, again, inverse. Theta is equal to the inverse sine of all of that. 200 times sine of 135 over 511. And so theta is going to be an approximation, and that's going to be approximately 16 degrees. Let me draw that better, 16 degrees. Okay, so now we have an angle. So this angle here is 16 degrees. Okay, now how would I express this angle as a quadrant bearing? Okay, so I'm going to have to kind of sort of draw a little bit of quadrant here, north, south. So I'm not going to start off with south. That'll be too big of an angle. So I'm going to go with from the north, from due north, going to my resultant vector. Well, that is going to be 90 degrees minus 16, right? So we calculated theta was 16. So if I take away 90 minus 16, that's going to be 74 degrees. This angle from north going to my resultant, that's going to be 74 degrees. Okay, we know that because going from north to east, that's a 90-degree angle. So I take away 16 from that, I get 74. Okay, so my concluding statement is going to be the resulting force is 511 newtons at, remember quadrant bearings always start with either north or south, so we're starting with north, sweeping 74 degrees toward the east. Okay, and so that's my concluding statement for this problem. So we've just successfully added two vectors in a problem that, and those two vectors were not 90 degrees to each other, so we had to use our cosine law and our sine law. Okay, so when two or more forces act on an object such a way that the object does not move, the object is said to be in equilibrium. Okay, so maybe you've seen that term before in science class, physics, maybe even chemistry, right? Equilibrium. So in physics, we talk about equilibrium where the object does not move. It could have forces acting all over the object, but the object still does not move because the forces cancel each other out. So an example of that is finding the equilibriant. The force is equal in magnitude, but opposite direction to the resultant force. So for example, if I had F1 and F2, these two forces that you see here, F1 and F2, if I just kind of translated F2 over here, connected them head to tail with my F1, I can now add them, F1 plus F2, leaving me with a force that looks like this, F1 plus F2. Okay, and it turns out that this force, let's just make this let's make this green. Okay, there we go. This resultant force is equal to f of 3. I should actually make f3 a little bit longer. So let's say f3 is just a little bit longer, make it to match the magnitude. Okay, so f3 is equal to the opposite of f1 plus f2. Okay, so there's my f. So this is my f3 force. Now, if I added f3 with f1 and f2, if I add all three forces together, the result would be 0. So meaning whatever object, think of this as object here, right here in the middle, whatever object I have there, if I have three forces pulling on it, and it just so happens that these three forces, F3 is just the opposite of F1 plus F2, all forces will cancel out, and the net effect is zero movement, zero acceleration. Okay, so that's what we call the equilibrium. Equilibriant. So sometimes we'll be applying forces like F1 and F2, and you'll be asked, okay, what would the equilibriant have to be in order for that object to be in equilibrium? Okay, so in other words, sometimes F3 will be that resultant force we have to find, a very specific resultant force, which would just be opposite of what is the other forces. So when solving for the equilibriant, it is the opposite vector of your resultant from adding all other forces. Okay, so keep that in mind. So example number 3. A scoreboard is being suspended by two cables that make angles of 35 degrees and 45 degrees with the ceiling. The scoreboard weighs 3,500 newtons. Determine the tension in each cable. Okay, so let's draw a little picture to help us understand this problem. So I'm going to have a ceiling. Okay, let's draw a ceiling. Right, I'm going to draw a flat horizontal line. Okay, there's my ceiling. Okay, right, and I have a scoreboard being suspended by two cables that make angles of 35 and 45 degrees with the ceiling. Okay, so let's draw two cables attached to a scoreboard, and I'm not gonna. Well, let me see if I can make the angles more precise. So we have an angle of 35 degrees. Okay, that's close enough. And an angle of 45 degrees. All right, that's close enough. Okay, there we go. And there's my scoreboard. That dot right there is going to be my scoreboard. Okay, and I'm just going to fill this in 35 degrees. And over here we have 45 degrees. Okay, and the scoreboard weighs 3,500 newtons. Oh, okay, well, we have a force acting down on the scoreboard of 3,500 newtons. So let's draw a vector for that, 3,500 newtons. And we know weight pulls things down, so straight down, that's where I'm pointing my vector, 3,500 newtons. All right, so I have a triangle here. Determine the tension in each cable. So each cable has a tension. Let's call it T, my vector T1 for the left one and T2 for the right one. Okay, so you have two vectors here. And which directions are these vectors acting? Well, they are acting opposite to the weight. So here, there's a vector keeping the scoreboard harnessed to the ceiling, right? So they're going to be, my arrowheads are going to be pointing up, right? So that it counters the 3,500 Newton force going down, okay? So you can see here we sort of have this triangle, right? We have a little triangle that we can use to solve this problem, okay? And I'm going to just see if I can find some more angles, right? 35 and 45 together make 80, which means the remaining angle here, this one is going to be 100 degrees, right? So the sum of the angles inside of a triangle is equal to 180. So 180 equals 100 plus 35 plus 45, right? So that third angle there is 100 degrees. Okay, so I'm going to now kind of, we have these vectors here. They're all attached tail to tail at the very center of this scoreboard. So I'm going to just kind of redraw the diagram into like a vector diagram, proper vector addition diagram. So I'm going to, now, as an equilibriant, right? Remember, to find T1 and T2, I got to find what T1 and T2 both have to add up to the opposite of 3,500 newtons, right? So, because this is what are the forces that balance it out? So I'm going to just say, okay, so T1 and T2 have to add up to 3,500 newtons pointing up, right? Because that's if you have an object 3,500 down, okay, to keep that scoreboard in place, you need a force acting up, 3,500 newtons. It's Newton's law, right? Whatever force acting on an object has to be balanced by an equal and opposite force. So that's what it is, right? 3,500 balanced with 3,500. So this one comes from the weight of the scoreboard. This 3,500 pointing up has to come from the two cables holding it up. Okay, so my two cables holding it up. Let's draw them head to tail. Let's draw T2 first here. Okay, so T2, 45 degrees approximately. Okay, and then T1 is 35. All right, close enough. There we go, 30. Okay, so there's my arrow. Okay, so there's my T2 over here, and here's T1. Okay, now the arrows are connected head to tail, and I'm going to now. I have to remember what angles are we looking at here? So, okay, so let's see if I can recognize how to do this. So I have a little. Let's use red here. I have a Z pattern, right? Z pattern. So this is going to be 45. If I translate this to the diagram here, well, okay, there's going to be a 45 here. This is also going to be 45. Okay, so that together makes 90. That's my L shape I see right there. So there's 45. Where will be my 35 degree angle, right? So if I have 35 degrees there, that's kind of like saying, okay, I have 35 there. But then on the inside of my triangle, it's going to be 90 minus 35, right? So 90 minus 35, that's 55 degrees. So inside my triangle is 55 degrees. Okay, and then if I do the 55 and 45, so 180 minus 55 minus 45, the remaining angle is going to be 80 degrees. So there, this angle here is going to be 80 degrees. Okay, so I've sort of finished recreating, creating a vector triangle, right? So now I have vectors that are connected head to tail, right? Head to tail, tail, and then my resultant is 3,500. So we're working with knowing the resultant, but how do I figure out the two tensions in the rope? So for this, I have the angles. I have one known side. So, okay, if you have one known side and its opposite angle, you could proceed to use the sine law. So it's going to use the sine law here. Okay, and the sine law says, well, if I have vector t1, okay, divided by its opposite angle, the opposite of t1 here is 45, so sine of 45 degrees. That's going to equal, okay, so we know 3,500 newtons over the sine of its opposite angle, sine of 80 degrees. Okay, and if I solve for t1, so t1, the magnitude equals 3,500 times sine of 45 over sine of 80, and that's, and make sure your calculator is in degrees, okay, and then your answer will be approximately 2,513 newtons. Okay. Similarly, we can apply the sine law for t2. Okay, so let's say t2, that vector's magnitude. If I divide that vector magnitude by its opposite angle, sine of 55, that's going to equal, well, don't use 2513. Use the one that we know. We know for sure. Because if you made a mistake with 2513, you're going to be making a mistake with t2. So we use 3,500 over sine of 80 degrees. And the result, so if I solve for t2, let's just fix that. So t2, magnitude of t2 equals 3,500 times, if I bring the sine 55 over, we times sine 55 over sine 80, and that's going to equal 2,911 newtons. Okay. So those are my two tensions in the rope, and we already know the angle they're acting, so there's no need to look for that. So simply in a question like this, here the answers I'm looking for are just the two magnitudes. Determine the tensions in each cable, just find the magnitudes. Okay. Moving on to our next problem, example number 4. An airplane is flying 560 kilometers per hour on a heading of 340 degrees. So keep in mind, that's not a quadrant angle, that's a true bearing. Okay. And we have the wind blowing at 140 kilometers per hour from the east. Okay. Draw a vector diagram of this situation. And part B, determine the ground velocity of the airplane. So here's our vector diagram. I'm going to draw a diagram. Let's draw north, south, east, west first. Okay. There we go. And now I'm going to draw my airplane heading 560 kilometers per hour on a heading of 340. So let's think about that for a moment. 340 degrees. So starting from due north, okay, we're going to go all the way around to 340 degrees. So where do I stop, right? So the whole thing's 360, right? So 360 minus 340 is equal to 20 degrees. So 20 degrees just from the left side of the north, right? So I'm just going to stop here at 20 degrees. Well, which should be probably 70 over here on my ruler. Like that. Okay, so there's my airplane. Vector for my airplane. Okay, so that's heading on a heading of 340 degrees. So if you want to you can, I don't need to, like, I could show that this is 340, okay, but I don't really need to. What I really care more about is the fact that this is going to be 20, okay, and but more so when I draw the rest of the diagram, everything will become more clear. So the rest of the diagram is going to look like this. So I'm going to take my ruler again, and we have a wind force, right? A wind blowing at 440 kilometers from the east. So if this point here is my airplane, okay, airplane's traveling in one direction, one speed, but I have a wind force acting on this airplane. Let's use blue here. Okay, there's my wind force. And that wind force, oh, I shouldn't have drawn it so big. Let's make it a little bit smaller. Okay, let's make it a little smaller. Because, the airplane's at 560. The wind force is only like 140. So they're a little bit, there we go. Okay, so there it is. There's my vector. Okay, and so this first vector I drew here, that's 560. The second at kilometers per hour. The second vector here is only 140. So 140 kilometers per hour. And then the resultant vector. Okay, let's draw the resultant vector. I'm going to draw a resultant vector like this. Okay, let's use a dashed line. Here's my resultant vector. And it's nice. The first two vectors are already connected head to tail. And so then my resultant vector, I can easily connect it from head to tail, the tail from one end to the head of the other. Okay, and so there's my resultant vector. So R, okay, and instead of this 20 degrees, right, you see this 20 degrees there? I'm going to just kind of like erase, oh no, I erased the whole thing. No, that's small eraser. Let's try a small eraser. There we go. Okay. So instead of saying 20 degrees, why don't I add the 90 degrees to it, right? So I'm going to add the 90 degrees like this. Add all of that, and let's call this 110 degrees. Okay, so it's because what we have here is a triangle, right? We have a triangle. If you don't see it, here it is. Here's a triangle. We have the angle between two sides. Okay, if we have the angle between two sides, then I can use cosine law. Okay, all right. So I'm just gonna clear up all that clutter if I can. Oh. Okay, so we're going to use cosine law. So SAS, side angle side, cosine law. Okay, and so the cosine law says, well, the resultant vector magnitude squared is equal to the sum of the squares of the other two sides, 560 squared plus 140 squared, minus 2 times 560 times 140 times the cosine of the angle between them, cosine of 110 degrees. Okay, and then if you put that into your calculator and you solve for r, okay, and magnitude of r, don't forget to take the square root of both sides, the approximate answer will be 622 kilometers per hour. And I always suggest you pause the video and you try that calculation on your own to make sure you still remember how to do it properly on your calculator. Okay, and then we have the resultant magnitude for the airplane. So the wind's blowing, the airplane's flying, and the combination makes the airplane go in a different speed and directions. So the wind's kind of pushing the plane to go faster. So it's going faster at 622. But the plane is not going at a heading of 340 anymore. It's going at a different heading, right? It's going the heading of the resultant, and we got to find that angle. So what's that angle? Well, on my diagram here, I'm going to look for this angle right here. Let's call this one theta. Okay, it's inside my triangle, so we need that. So I'm going to use the sine law here. Sine of theta divided by its opposite side. The opposite side is 560 equals, well, do we have any other angle? Yeah, we do. We have the sine of 110 degrees divided by its opposite side, which we just calculated, which is the resultant, 622. And if I solve for theta, so theta equals the inverse sine of uh, if I move the 560, multiply it, so 560 times sine of 110 over 622. Okay, and again, do this on your calculator, verify that you get the same answer as I do. The answer is approximately 58 degrees. Okay, now, all right, how do I express this angle properly in the context of this resultant velocity? Well, I'm going to this is now 58 degrees, okay? Now remember, okay, let's think about this for a minute. If I reposition the compass, here's my resultant, okay, and we just said that this angle here was 58 degrees, okay. If I went counterclockwise and I counted, okay, if I add 90 more, 90 more, and then 90 more, I get back to due north, right? So that's going to be 90 plus 90 plus 90 plus 58, which is 328 degrees. Okay, so I'm going to express my answer this time as a true bearing. So I can say here, therefore, the resultant velocity is 622 kilometers per hour at a bearing of 328 degrees. Okay, and that is my 90 plus 90 plus 90. That's 270 plus the 58. Okay. Alternatively, you could express it as a quadrant bearing. Okay, and if I'm doing it as a quadrant bearing, I'm gonna do it from north sweeping to the west, right? So I wouldn't use 58. I would use 90 minus 58. Okay, and that's going to be 32. So I would express this as north, starting from north, going 32 degrees to the west, right? So remember, this is the 58. This is going to be 32. Okay, so you start from north, sweeping to the west, right? So that's going to be 32 degrees. Okay, so that's example 4. Let's look at one more example. Example 5. A canoeist leaves a dock and paddles her canoe at an angle across the river. The current is flowing, where's my number? At 3 kilometers per hour. The resultant velocity of the boat is 5.4 kilometers per hour downstream in a direction that forms a 15-degree angle with the adjacent shore. So part A, draw a vector diagram of the situation. All right, so again, a lot of these problems, the hard part is, well, what does this diagram look like? So you have to be very careful about what we're drawing. So I'm going to draw a little river here. All right, so we're doing like a bird's eye view of a river from top down. Okay, and again, so from one end of the river, let's say, okay, from this side here on the shoreline, okay, he's going to take the boat and paddle, right? So what's happening here? There's a current flow of 3 kilometers per hour, but the boat is moving, has a resulting velocity of 5.4 kilometers per hour downstream that forms 15-degree angle. So I'm going to try and make a 15-degree angle here. Like that. Okay, and that's going to be, let's make this shoreline flat line. Okay, maybe I erase the blue part. Okay, let's erase the blue part. Okay, there we go. And let's draw a flat shoreline so I can better draw some angles here, right? So, okay, there we go. And and this is 15 degrees. Okay, and that's a vector going at 5.4 kilometers per hour. Okay, and then the river, yeah, we have a current flowing at 3 kilometers per hour, and it's downstream, right? So we're going downstream. Let's say the river is flowing this way. Okay, so I have 3 kilometers per hour. So it's going to be a smaller arrow than my 5.4. Okay, so there's my arrow going 3 kilometers per hour. Okay, and that's in the direction of my river flow. All right. So then so the question is, if 5.4 is the resultant velocity, meaning after you take into consideration where the canoe is paddling and the river flowing, then what I'm looking for is this vector over here. I'm going to draw it in. I'm looking for this vector right there. that red vector. Okay, so in other words, this is the vector where the canoeist starts paddling, right? That's this red vector is where the canoeist starts paddling. The 3-kilometer river is pushing the canoe, and combined with this paddling ends up being this 5.4 kilometer resultant velocity. Okay, so you kind of have to really be careful with the language in the word problem and try and interpret it as precisely as possible. Okay, so this is the vector diagram. Let's call this red one. Let's call this the resultant now. I guess we're going to solve for that one. Okay, and so there's my vector diagram. Part B says determine the canoeist's velocity relative to the water. Okay, so to determine that velocity, we recognize that we have a triangle here. Okay, I have a little bit of a Z pattern going on here. Okay, so we know inside this triangle here I have a 15-degree angle, right? That's a Z pattern rule. And well, I'm probably going to look for this angle here, theta. And we have two sides. We have two sides and the angle between them, the 5.4 and the 3 kilometers. The angle between them is 15 degrees. Therefore, I'm going to use the cosine law. Okay, so I'm going to say here that the vector I'm looking for, r squared, the magnitude, is equal to 5.4 squared plus 3 squared minus 2 times 5.4 times 3 times the angle, the cosine of the angle between them, cosine of 15 degrees. Okay, and then I'm going to solve for r. Okay, and if I solve for r correctly, the answer should be 2.6 kilometers per hour. Okay, and so that says here my canoeist is paddling at 2.6 kilometers per hour in that direction. When you combine it with the 3-kilometer river, the resultant is 5.4 kilometers per hour. Okay, and notice it's not a straight up addition. You don't add 2.6 plus 3 to get 5.4. It's not like that, right? It's because of the angles that we're playing with here. All right. Okay, so what is that angle? Well, I need to find theta using the sine law. So sine of theta. So if theta is there, the opposite side is 3 kilometers. So sine of theta over 3 kilometers per hour equals, what's the known angle we have? We know the angle 15 here. And so that's sine of 15 divided by its opposite side, which we calculated to be 2.6. And if I solve for theta, like before, we should get a theta of 17.4 degrees. Okay, but that's the angle inside my triangle, right? What I want to do now is, well, I need to determine this angle with relative to the water. So the water is flowing horizontally. So if I think about this, right, here's my resultant 2.6, okay, and the river is horizontal, okay, and so I have the 5.6, the 5.4 kilometer one here. So this angle here is 17.4, and we know this angle here is 15. Then the angle that my canoeist, the 2.6, makes with the water is going to be the addition of those two angles, right? So 17.4 degrees plus 15 degrees is equal to 32.4 degrees. Okay, so my concluding statement, I'm going to say the resultant, or therefore the velocity of the canoeist, is 2.6 kilometers per hour at, now the way I'm going to express this is 32.4 degrees, okay, relative to the adjacent shoreline. Okay, but alternatively, you can express it as a quadrant bearing starting from due north, sweeping to the east. So in this case, I'm going to just bring us back to this diagram. Imagine your northeast compass. Well, you can say, well, the angle I'm looking for is this one right here, 90 minus 32.4, which is 57.6. Okay, and that would be your equivalent quadrant bearing. Okay, although it's it's 57 point. Did I say 57.6? Yeah, 57.6 degrees east. Okay, but it doesn't make so much sense because we're looking at a top-down view of a canoeist traveling down a river. So, I'll take the answer if you express it like that. But there are other ways to express the angle, and as long as we specify, okay, 32.4 relative to what, it's relative to the adjacent shoreline, and that's this shoreline right here. Okay, or this one right here in this diagram. All right, so I've given you some examples of how we can apply sine law and cosine law in adding vectors. The hard part in some of these problems is trying to figure out how to draw or how to interpret the wording in the problems to draw the proper diagram. And once you have the proper diagram, then you know how to add the two vectors. And that takes practice. So have a look at the practice problems. Have a look at some more examples that are on these pages here. So read the examples. Not all of my examples are the same examples from the book. So read the book for extra examples. Really try and understand how to add two vectors given the situation, given words. All right, and then try the practice problems, as many as you can. The more practice you get at this, the better you get at it. And I'll take up some problems in class if we need to. All right, and that ends this